This is video number 6 in the series on the reinforcement of concrete slabs. This video deals with the reinforcement and detailing of slabs. What type of basic control is needed and in which limit state? In the ultimate limit state, we determine the reinforcement, the bending moments, normal force, shear force, and punching shear is checked. In SLS, the serviceability limit state, we check the deflection in SLS Q or F. We check the crack width in SLS Q, the stresses in SLS Q, F, and K, and fatigue. The reinforcement of a slab is, like we have said before, the same as for beams, but it is with like a beam, but with a width of 1 meter. So we use the reduced bending moment μd. From that on, with the tables of concrete, you convert it into reinforcement in millimeters, square millimeters per meter. The difference now is that in the conversion of needed reinforcement, you have two parameters. It is the number of rebars and the diameter. And it's the number of rebars per meter slab. This means that we can express now the reinforcement as, for instance, 3 rebars 10 per meter, or you can also say diameter 10 with a spacing of 333 millimeters. So, or you specify the number of bars, or you specify the spacing. From so far, it's straightforward. There's nothing new, in fact. Also for anchorage length, it's exactly the same as for beams. And if you take the anchorage length, for instance, for a concrete grade of C25, you end up with an anchorage length of 40 times the diameter. For a higher concrete grade, you are arriving at 36 times the diameter. Lap length is also the same as for beams. And for a concrete grade of C30, the most commonly used, you end up with 54 times a diameter. Just to give you a feeling of how to convert required reinforcement into practical reinforcement, then you see here some figures commonly used. If you have 250 square millimeters per meter, that means that you have 5 diameters 8 per meter. For 400 square millimeters per meter, you end up with 5 diameters 10 per meter, and so on. So this table gives you a clear indication how to convert it in a quick way. The same exercise is done for anchorage length for diameter, bar diameters 8, 10, 12, 14, and 16. And then you have here an impression what the anchorage length will be. This is done for concrete grade C30-37 in good conditions. If you do not have good conditions, for instance, for reinforcement on the top of the slab, then you have to divide the anchorage length by 0.7. For lap lengths, it's the same as anchorage length, but times 1.5. The spacing, the maximum spacing of the rebars for slabs, you must make a distinction between main reinforcement and secondary reinforcement. The main reinforcement in general, the spacing must be smaller than 2.5 times the slab thickness and must always be smaller than 400 millimeter. And for the main reinforcement, when you are at the maximum bending moment M, then the spacing must be smaller than 1.5 times the thickness of the slab. And to distribute loads, you should have a spacing less than 250 millimeters. The secondary reinforcement is always smaller than 3 times the depth of the slab and smaller than 450 millimeters. And at the maximum bending moment for the secondary reinforcement, it should be smaller than 2.5 times the depth and smaller than 400 millimeters. The 400 millimeters, it's coming from the size of your foot. So if you take bigger distances between two consecutive rebars, you have the danger of hurting your feet. From a slab thickness starting from 160 millimeters, then the combination of 400 and 250 and 450 and 400 is dominant. So and as a rule of the thumb, for a main reinforcement, in practice situations, you take a distance between the rebars smaller than 250 millimeters, and for the secondary reinforcement smaller than 400 millimeters. Video 6 is about one-way slabs. So in principle, you only need the reinforcement in the main direction. But this is not the case in reality. You always need a redistribution reinforcement, which is a reinforcement perpendicular to the direction of the main reinforcement. It's also called the secondary reinforcement. And the reason for that is that there are always bending moments perpendicular to the main direction. This is because of the torsional bending moments in the corner of the slab. Then you want to spread out the loads. Uniform distributed loads are not in reality uniform distributed. They are on some places there are loads, on other places they are not. So you have to distribute, to spread out those loads. So that's why you need secondary reinforcement. Shrinkage, it acts in all directions. So you need also reinforcement for that. And minimum reinforcement for crack control and brittle failure, you need it in the both directions. So that's why you need redistribution reinforcement. Non-uniform loading can lead to bending moments perpendicular to the main direction. We should never forget that. For the secondary and redistribution reinforcement, we should take 20% of the main reinforcement, or 1.2 times the calculated reinforcement. If calculated reinforcement is smaller than the minimum reinforcement, then you take 20% of the calculated reinforcement in a finite element method. It should be greater than the minimum reinforcement for brittle failure and crack control. And of course, you should take the calculated reinforcement, which is obvious if the calculated reinforcement is larger than the minimum reinforcement. We said that the secondary reinforcement is 20% of the main reinforcement. Where is that 20% coming from? Well, we can make a very basic reasoning. The bending moment in the second direction is my. It's equal to the stress in this direction times the bending resistance. The stress law of Hooke is equal to the modulus of elasticity times the strain, but we know that the modulus of elasticity is the same in the both directions, or it is an assumption, it's a homogeneous material. then we know that the modulus of elasticity is the stress in the x direction divided by the strain in the x direction. Or we can rewrite it as follows. We know that the coefficient of Poisson is proportional to the rate to the strain in the y direction and the x direction. So if we introduce this, and then we know that the proportion of the bending moments is equal to the proportion of the resisting bending moments. It means that redistribution reinforcement, this is the secondary reinforcement of bending moment, and this is the first, and the redistribution reinforcement is proportional to the ratio of the resisting bending moments. And when the resisting bending moments are equal to each other, then obviously the proportional of the bending moments in x and y direction is equal to the Poisson coefficient, and which means 0.2, which is 1/5. That's where the 20% is coming from. It is just the coefficient of Poisson on the condition that the bending resisting moments of the resisting bending moments are equal in x and y direction. It implicates that there is no redistribution reinforcement or secondary reinforcement needed, in fact, if the coefficient of Poisson is 0 or if the resistance in the y directions is 0. There is also a 50% support rule, and it states that the reinforcement, the tension reinforcement at the support must be at least half of the reinforcement needed at midspan, or the maximum sagging bending moment. Take care, the reinforcement at the support is in fact the maximum of those of 4 reinforcement ratios or 4 reinforcements, which is of course the minimum reinforcement must always be bigger, larger than the minimum reinforcement. The reinforcement which is calculated, for instance, when the support is fixed or clamped. It must also be bigger than the reinforcement that is needed to take up directly the reaction force into the steel. So it's a shear force, but only for the shear, the pure shear in the rebars. And of course, the reinforcement, the maximum reinforcement needed in the span of the slab divided by 2. The reinforcement needed for shear is the total force acting at the support must be covered by pure shear capacity of the reinforcement. This is to avoid total collapse of the slab. Where is this coming from? Well, we can make a small calculation. The minimum reinforcement supports at least half of the main reinforcement at midspan. Just taking isostatic beams to make it life easy, isostatic beams with uniform distributed loads, then we know that the reaction on the support is the uniform distributed load times the span divided by 2. The reinforcement needed for shear at the support is then the reaction divided by the maximum allowable stress, and the maximum allowable stress for shear is the FID divided by square root of 3. And if you take the units Newton and millimeter, you have this formula. So the required shear reinforcement is uniform distributed load times the span divided by 504. The bending moment, maximum bending moment is QL squared over 8. The reinforcement in bending in the middle of the span due to the maximum bending moment is then equal to, if you rearrange the terms, it's equal to QL over 221. In this conversion, we have L over D. Yeah. So we made a conversion. Is it slenderness L over D? We know that for a slab it's between 14 and 20. We have taken here 14 to arrive at that. Then you will see that this is almost half of it. So you see that the reinforcement at the support must be at least half of the reinforcement at midspan. It's just an indication, it's not a proof. We will now give an example. What is the needed reinforcement to supports? It's a one-way slab. It's clamped on the one side and simply supported on the other. It's a 6-meter span. The depth of the slab is 250. The effective depth 200. Concrete quality is 30 megapascal. The steel quality 500 megapascal. And the load is 15 kilonewton per meter. The minimum reinforcement, it's like with beams, is the same thing. So the minimum reinforcement for brittle failure, we fill in those formulas and we see that in total we will need 300 square millimeters per meter. It must be bigger than 260, so that's all right. So we have 300 square millimeters per meter. That's the minimum reinforcement that's needed for top and bottom. So this is a top and bottom reinforcement. At the sagging bending moment for this slab is equal to 38 kilonewton meters per meter. And when we convert it with the concrete tables, we have the reduced bending moment of this and the zeta equals to 0.96. Then we arrive at a needed reinforcement at the span. The sagging bending moment is 455 square millimeters per meter. At the support, when the support is fixed, we know that the bending moment there is 18QL squared. It's 67.5 kilonewton per meter. We convert it through the concrete tables into a reinforcement and we need 826 square millimeters per meter. The reinforcement that we now need at the support, at the fixed end support, the total reaction force is 56 kilonewton per meter. And the reinforcement we need for that is the reaction divided by the maximum allowable shear stress, and it gives us 224 square millimeter per meter. At the support of where the slab is hinged, then this is the reaction force, is 33 kilonewton per meter, and again the reinforcement we need for shear is 134 square millimeters per meter. The needed reinforcement at the support at the fixed end on top of the slab, on top of the slab, is then the maximum of the reinforcement in the span, the minimum reinforcement, the calculated reinforcement, and the reinforcement needed for shear. So this means that we need 826 square millimeters per meter. On the bottom of the slab, near the end where it is fixed, we do the same calculation. It is the span, half of the reinforcement of the span. The minimum reinforcement, the calculated reinforcement is 0 because there is no sagging reinforcement, sagging bending moment there, and the minimum reinforcement needed for shear is 224. So in total of 301 square millimeter per meter. You see now the minimum reinforcement here is dominant. And now we can look at the support, which is not restrained, but at the other side, at the other support, it's also the same formula we apply. It's the maximum of the span reinforcement, the minimum reinforcement. The calculated is 0 because there is no bending moment there, and the shear, the reinforcement needed for shear is 224.
So we end up with 301 square millimeter per meter, which is the minimum reinforcement. And at the bottom, the lower reinforcement, we make the same reasoning, and we have also a minimum reinforcement. So this is how you calculate the reinforcement that has to be on the level of the supports of the slab.